Hey, it's Don here from the board. Thank you for coming along and checking out this video on systems engineering. Now, I'm going to break this concept of systems engineering into a couple of different videos, I think, just because it might get a little bit long to be in one video, but we'll see how we go. So, what exactly is systems engineering? And of course, if it was something that I could explain just in one or two sentences, there probably isn't really much point in me doing this video. However, at a very high level, top-down approach, systems engineering is all about the process that is required, maybe, or that is utilized to develop a robust, functional system. Now, I realize it's a little bit redundant to be talking about a system when you haven't really defined anything, but we'll get down to that. So let's talk about definitions. What exactly is a system? Well, a really simple way of describing it is that a system is something that is made up of a series of systems or subsystems. Subsystems can be actual discrete systems with complete subsystems underneath them as well, or they can be simply down to the lowest component level where it doesn't have anything else that you would describe as a system within it. And of course, trying to keep this discussion and this sort of information about systems engineering keyboard related, if you want to really look at it, you could say, for example, a spring is a component, whereas a mechanical switch is a system. The reason why it's a system is because it's composed of the stem, the spring leaf, the spring itself, and the housing. So it really just comes down to how you define your various different functional blocks. But we'll get to that as well. So let's crack on and start doing some drawing and explaining and diagrams and so forth. So I'm just going to switch off this face camera because I'm going to be looking downwards at my little whiteboard here as such, and hopefully we'll be able to put something up on systems engineering. Okay, the first thing that's really important to understand about systems engineering is that systems engineering always comes from a requirement of function. Now, quite often people get confused about systems engineering and they can be blindsided by the fact that they only know systems engineering within the field that they work or that they've encountered it. What I mean by that is, for example, software engineers will talk about systems engineering. However, mechanical engineers, electrical engineers, design engineers, they'll also talk about systems engineering. And there is often misconceptions that they are different, but they're not. Systems engineering as a process is exactly the same. The application just tweaks and adjusts certain things. And so what I mean by that is, in a software systems engineering, you still have components and subsystems, however, they tend to be things like subroutines. They tend to be, programs or encoding or loops, logics, that kind of thing, compared to, say, a mechanical system which uses systems engineering, such as a mechanical switch. Now, looking at it from, say, an electrical engineer's point of view, you would still have systems engineering because you have things like, black box devices which contain multiple components that cause a system to undertake a particular function and purpose. So with all systems engineering, there must be a requirement. This requirement comes from whatever it is that you're after. It could be a customer saying to you, I want a product X, Y, and Z. It could be internal. It could be your boss coming to you as a program team and saying, I need you guys to write me a program that will do X, Y, and Z. There's always a requirement, and that requirement drives function. Now, these requirements lead to functions because something that you require has to do something. And that is the core aspect of systems engineering. Now, this is really only to start off with the broad overview before we start getting to a little bit more detail. Now, once your function is actually defined, you would go ahead and you would do functional analysis. For the purposes of determining what components exist that you need to create, or if something already exists that you can utilize. So rather than reinventing the wheel, if something out there already exists, why not take that and implement that because it serves the function that you're after? And of course, relating back to keyboards, why would you redesign a switch if you were trying to build a whole keyboard when you could just go and get known designs of switches that would work and plug straight into your particular requirement and function? Now, this is all above the line. Now, the method that I'm talking about here is commonly known as the V method. There are many different methods of systems engineering, and this is just one of them. They all have their advantages and disadvantages, but this is one that I am the most familiar with. And the V system, the V method, looks like this. And it's called a V, obviously, because it's in the shape of a V. When we go down the line, this is what's called decomposition. When we go up the line, this is what's called integration. How this works is, once your functional analysis has determined all of your components or your subsystems, you start to decompose your components and subsystems. We run with what's concept known as a black box to white box. So we go a black box to a white box on a decomp side, and then from the integration side, we go from a white box back to a black box. And what's really important on both sides is they have to match. On the integration side, what's also really important is what's called validation and verification. However, to put it really simply, what this means is that it has to be testable. Okay? One thing that a lot of people tend to miss in regards to systems engineering and designing their system running through any of these type of methods is that they don't spend enough time hashing out requirements. Because if your requirements aren't very rugged, if you haven't defined your functions very well and very cleanly, it makes it very difficult after you've gone through the decomposition and you're in the integration phase to be able to validate, to be able to verify, and to make what you're doing testable. And what I mean by that is there's things that you can test, but just because they're testable doesn't actually tell you that you've achieved what you want. So if we take the switch as an example, the function could be as simple as saying it needs to actuate and produce a signal. So there's a signal, right? But then down here, you can say, well, I can close the switch and I have a signal. Tick. But that doesn't mean necessarily that that's a good signal. There is no talk about its quality of signal. There's no talk about its, debounce time. There's no talk about, how good that contact is or how long that signal period is, and so on and so forth. And so if you don't do that correctly up here, you end up with a bit of a mess down here. And that kind of leads me to going forward into talking about the top section here, at least to start with, on building your requirements and your functions. So let's clear this off. So if we come up with, say, a keyboard OEM company, well, let's just call it the board keyboards, All right. So the board keyboards walks into a meeting room and says to their systems engineers, their designers, you know, I want you guys to build a programmable keyboard. I want it to be aimed at programmers, designed for coding. Okay? So the requirements that they're going to set out will say, well, it's a keyboard. Pretty obvious. So I'm just going to say requirements. Okay? It's a keyboard and they want it to suit programmers. And that's it. And they walk out the door. How would you be able to build a proper product, a proper keyboard to suit these requirements? It's really, really difficult. Depending on who you talk to, you're going to get different answers. And this is where the use of outside help, the use of talking with subject matter experts becomes key, becomes critical, because you don't know exactly what these two things could entail. If we simply look at a keyboard, missed the A there, what have we got? You can talk about size. What size keyboard are we looking for? You can talk about switch types. You could talk about lighting. You could talk about peripherals. So what I'm talking about there is things like a USB hub on it. Or, you know, media keys. And so on and so forth, right? These are all details that design has to consider, but was not given to them. And then if we look at suiting programmers, what exactly does that mean? What do programmers want that would be suitable for them? Does that mean, you know, layouts? Are we talking, you know, programmable layers? So on and so forth. So if you don't have a really clean idea, if you don't have a really well thought out set of requirements, you're going to be stuck. Of course, normally when they do systems engineering, they would spend a lot of time on this because they would break it down into all of the particular details that they want. And it's not unusual for someone, while they're actually doing systems engineering, to have pages and pages and pages and pages, whiteboards filled, you know, lots of notes, simply because each one of these details has an implication further down the line. If you don't sort them out at the start, you may end up designing something that does not meet the requirements that you were asked for at the beginning. It's really important to be able to get inside the head of whoever it is that is asked for this design or product to get their vision. Their vision is really important, simply because each one of these details has so many different options that you might come up with something that's really fantastic, and then the person who's asked for this request will go, that's not what I wanted. Very important that you get it right. Now, once you've actually got the requirements that you're after, that's when you start breaking down their functions. And functions are also very important because it determines the components, it determines the black box, white box relationship, and it also determines how they can be tested. Let's go with something a little bit more exciting, shall we? Let's go with some purple. All right, so let's have a look at functions. Functions for a keyboard is to input keystrokes. Okay, is that all a keyboard is meant to do? Is that all that we want this keyboard to do? Well, you could say one of its functions that you want is to be, it's programmable. What's another function, right? Now, you might say, well, these requirements and functions, they're replicating. And they can be. There's no reason that a function and a requirement don't overlap. But you do look at them slightly differently. And the next example that I'm going to talk about is lighting. So now, when you talk about lighting, under requirements, they might say, well, I want it to look cool. I want it to have RGB. Okay, and that's lighting. But what is the actual function difference between a requirement for RGB and the function of RGB? It has to light. It has to produce light, right? It has to have colors. And it has to be correct colors. You know, it has to have modes. It has to have brightness. So all of these are functions, sub-functions of a simple requirement, which is to have RGB lighting. Now, if you don't actually define every one of these layers of sub-functions, then you might end up with lighting, RGB lighting, but once again, it doesn't meet and match the vision that your customer or your requester wants. So it's really important to be able to get all of these down. Okay, so there's just an example of some of the functions. And, well, we can take this and we can break it down into functional analysis. And functional analysis is the last sort of point that you need before you start getting into the V diagram, because it's what determines your assemblies, your components, your subsystems that you're actually going to be doing the white box, black box work with. Okay? So let's just clear that and give ourselves a little bit more space to work with. All right. Functional analysis. So let's take RGB lighting. Well, how do you get RGB lighting? What is RGB lighting? And this is what you would do in a functional analysis phase. Well, you would say RGB lighting produces light, right? It emits light. So it emits light. It emits color. Okay. Well, how do you get light? How do you get color? You need an LED or a Cree or, you know, diodes, light emitting diodes, well, which is really what an LED is anyway. But at the same time, you do need circuitry, right? So you need a control unit. You need power. So let's get rid of the Cree, because we're just going to go, well, we'll go with an RGB LED, right? Make it a little bit easier, okay? So when you start breaking down in your functional analysis, to produce this, it has to do this, and how it does this is with these components. Now, so we're just going to box that off. In order to understand what we're doing then, you need to start building your physical allocations. So this is a functional allocation. And because we're working with something physical, we also need to have physical. Now, when we look at systems engineering, for example, for software, though, that's a little bit different because they don't have physicals for most part. And so they would actually box it slightly differently, which is why I say systems engineering is tweaked depending on what you're actually doing with your systems engineering. So An RGB LED is, we're just going to start using a couple of different colors to make life a little bit easier. So here's my RGB LED, okay, and there is a physical line here. And then we have a control unit, and then we have power. Now, why do we do a physical allocation compared to having the functional allocation? And the reason is, you need to work out physically where these components live and how they're related to each other. And what I mean by that is, do you want a control unit by itself and then a power unit by itself? Because if you do, then you have to do a decomposition and integration, a V&V and test on 3 components. Or could you change your design somehow, change your system somehow, and say, well, you know what? I'm going to have my control unit and my power supply in one unit. And then it forms that relationship. If you do that, then you only have one unit that you have to V&V and test. Is it better that way? I don't know. Is it worse that way? I don't know. Is it easier? Is it harder? All of these considerations are up for debate because it comes down to the level of detail that you want to go into, the level of maintainability, you know, if you're doing repairs or if you're doing spares and so on and so forth. Will they ever need to potentially replace that by itself or fix that, or the control unit or the LEDs, you know? Ideally, it comes down to the level of product that you want. So if this is going to be a consumer grade level, there's no reason why you couldn't put all 3 of them into one. You could have an RGB, LED, terrible handwriting, the control unit, and the power supply all boxed into one. However, if your LED fails, then you have to replace this whole unit. Is that very friendly? No, but it might be more cost effective to produce. Will it upset your customers? Maybe. I don't know. It depends on the level of the product that you're pitching. You know, if you were making this to be a very reliable, a very customizable system, or something that your users can self-repair and so on and so forth, you wouldn't do this because they would get upset because then they're going to have to take out that LED and that control unit and the power supply all at the same time to replace just one component that has failed. However, if you break it up like I had earlier, and you say, well, here's the LED, there's the control unit, there's the power supply, and you have them as separate components, then at any given time, if one of these fails, let's say, the power supply craps itself, then you could pull that out, put in a new power supply, and it's good to go. And so this is why the physical allocation actually matters. For most consumer goods, they will put this physical allocation down to the lowest cost-effective level. For goods that tend to be at a higher spec, so things that have very good warranty, or they're designed to last for very long, or they're designed to have very low maintenance, they will be designed in a particular fashion that will allow a technician or a maintainer or a service guy to come along to be able to check components individually and then either remove and replace or repair. And it may be a repair matter. Is it easier to repair a power supply all by itself or a power supply that's integrated with your control unit? I don't know, and it comes down to your design. So once you've actually decided on your physical allocation, that's when you would start going into your actual V diagram and doing your decomposition and then your integration phase. So where are we at the moment? I've just spent 25 minutes talking very quickly, I suppose, at a very broad general brush. And so we've got requirements, we've got function, we've got function analysis, and that's all above the line. And then we will have our decomp with our black box to white box, and then our white box to black box, V and V and test, which is part of our integration. Okay, so we've just covered that, and that. And I'm going to end that for this particular video, and we'll continue on in the next part on my very light level introduction to systems engineering. Thank you for checking out this video.